Okay, good evening. This is Professor David J. De Los Reyes. Okay, it's October 11, 2023. The time is, what time now? 1:07 a.m. Okay, my topic for this session will be alternating current machines, and this will now be lesson number 36. We are running smooth, so for those of you who are following my channel and following my topic on AC machines, we are now on lesson number 36. Okay, let's continue the discussion for tonight. Okay, let us start. The title for this morning will be AC machines, lesson number 36. And the title of the topic will be Y connection, voltage and current values. Okay. For a Y-connected transformer, what will be the relations of the voltages and currents? Or shall we say voltage and current relationships? These should be relationships. Okay. Why relationship? Because for Y connection, the phase voltage, the value of the phase values and the line values are actually different. And for a Y-connected transformer, whether it's primary or secondary, okay, the relationship of the phase voltage and the line current, okay, I will now give you the derivation before I will teach you the derivation. In general, for a Y-connected transformer, Y, the relationship of the voltage, capital letter B with the subscript double L, meaning line to line voltage, is equal to a factor of square root of 3 times the value of capital letter B per phase, meaning square root of 3 times the voltage per phase. Okay? This is a general equation. So, for as long as we are leaving the relationship of the line-to-line voltage with respect to the phase voltage is given by this equation here. That is, the line-to-line voltage will be equal to square root of 3 times the value of the phase voltage. Okay, I will try to derive later on. And for the current, the value of the phase current is equal to the line current for a Y-connected transformer, whether primary or secondary. Okay, so this is also a general equation. Like what I said, for as long as we are leaving the relationship of the phase current, okay, with respect to the line current, they should be equal. Okay, so the easy thing for a Y-connected transformer is that the current should be the same. Okay, just think of that one. And for the voltages, it will be a different story. That is, the line-to-line voltage is equal to square root of 3 times the value of the phase voltage. Okay, it is not times 2. Okay, it is not times 3. It is square root of 3. There must be a reason why it is square root of 3. That's why I'll try to bring out the derivation. Okay, let's proceed. Let's just consider for the meantime the secondary part of the three-phase transformer, which is connected in Y. So this should be the first winding, this should be the second winding, and this should be the third winding. And as you can see, the connection is Y. Right? Okay, let's try to label the figure so we could understand it. The voltage across this phase here is designated voltage per phase. And if we try to place the value in terms of the so-called polar form, because voltages here are actually complex numbers, right? It should be B angle 0 degree, this portion here. On this winding, okay, the value of the phase voltage in terms of polar form is the value of B angle of 120 degrees, right? And the voltage across this, the third phase, this is actually the neutral, right? The voltage on the third phase is actually B angle negative 120 degrees. Okay? Why is it 0 and this is 120 and this is negative 120? Because for three-phase system, okay, the induced voltages per phase are actually, meaning the magnitude are the same, but they are not, what do you call this, in phase with each other. Why they are not in phase? Because the angle of the first one is at 0 degree, the angle of the second one is at 120 degrees, and the angle of the third one is at negative 120 degrees. It was like this. This is voltage, right? The first one might be this one. Okay? That's A. This one. The third one, okay, they are not alive actually at the same time. This was ahead by 120 degrees. This is 120 degrees. So if this is 120, okay, the second one will be like this, right? And the angle difference here is actually 120 degrees. Okay? And the induced voltage on the third one, okay, the angle between them is 120, so this is actually 240, right? 0, 120, 240, okay? It is something like this, right? So this is B and this is C. They don't occur at the same time, okay? There was a lag behind by 120 degrees. When A is at this location here, okay, B will start here and C will start here. Okay? That's why if we try to express this voltage here in terms of polar form, it will be voltage B angle 0 degree. The next one will be voltage B angle 120 degrees. And the third one will be voltage B angle negative 120 degrees. Right? They are all what they call the sinusoidal, but they don't occur at the same time as they fluctuates. Okay? What will be next? If we try to designate this line here, the output line as A, line A, and this line here as line B, and this is as line C. If we try to get our voltmeter here, if we try to measure the voltage across this, okay, the voltage we are measuring here is actually BAB, and BAB is actually line-to-line voltage, because this is a line, right? So if you try to measure the voltage across this, we call this one line-to-line voltage, right? The next one, if we try to get the voltage between B and C, you put the voltmeter over here, okay? What you are measuring is actually, it's not the phase voltage, it's the line-to-line voltage. Okay? The third one, you measure the voltage between line A and line C, right? We still call this line-to-line voltage, right? So if we now try to compute for the value of this one in terms of this, okay, we will get the relationship of the line-to-line voltage with respect to the phase voltage. We'll go back to the vector diagram. The first voltage is actually at angle 0 degree. The next voltage is actually at 120 degrees. Okay? This is line-to-line voltage, right? So it should be the vector sum of this voltage here plus the voltage across this. Vectorially. So, okay, so we will use the so-called parallelogram method. This one here is parallel with this, and this one here is parallel with this, and the intersection will be the so-called line-to-line voltage, right? We add it vectorially. We don't add it, what they call this, realistically. It seems we are adding two real numbers. It is not. Because voltages are actually comprises of real numbers and imaginary parts. So we are adding it vectorially. So the vectorial sum of the voltage across this, which is this, plus the voltage across this, which is this, if we try to take the sum of this one plus this one, it should be this one here. Okay, it should be this one. And we call that one line-to-line voltage. Okay, let's try to take the sum. Because we know the specification of this one, it should be the magnitude of the voltage angle 0 degree, and this one here, it should be the magnitude of the voltage angle 120 degrees. So if we try to take the sum of this voltage here plus this vectorially, okay, it will be this one here, and if we try to bring out in our computation, it should be something like this. Okay, DAB. Okay, we call this one capital letter B with the subscript LL, meaning line-to-line voltage, and this should be equal to B angle 0 degree. It should be the voltage across this. The voltage across AB should be equal to this voltage here plus this voltage here. And the voltage across this is actually B angle 0 degree, right? And the voltage across the second winding is actually B angle 120 degrees. We are adding this one vectorially. That's why I told you under the study of AC circuit, it is the same. We could apply this to AC machines. We are adding currents and voltages vectorially. So if we try to take the sum of this one now, of course, if we try to take the sum, this is, sorry for that. This is polar, this polar, right? So we'll convert this to rectangular. Cosine of 0 is 1. 1 times B will be B. Sine of 0 will be 0. 0 times B will be 0. So the imaginary part is actually plus G0, right? For the first one. Okay? It's a pure real part, the first voltage. The next one, 120 degrees. You take the cosine of that one. A cosine of 120 will still be a 0.5. Okay? 0.5 multiplied by B. A sine of 120 will still be plus. Okay? Why is it plus? Cosine. Yeah, this is plus. Okay? For the imaginary part, the sine of 120 will be 0.866. This is multiplied by B. Okay? So, the rectangular equivalent of this one will be 0.5B plus J 0.866B. Right? Then we try to combine similar terms. Actually, we could remove the parentheses now. Right? It's not so complicated. We'll add up the real parts. B plus 0.5B will be 1.5B. This is G0 plus 0.866. This is just J 0.866 multiplied by B. We factor out B, so this is B. Okay. There is a 0.866 upward. There is a 0.5 here. This is J 0.866. So if we try to take the magnitude, okay, Pythagorean principle, or you take the ratio of this one, you take the value of the angle, you take the cosine, you divide that to the real part, what will come out will be 1.732. The resulting angle will be 30 degrees, meaning the angle of the vectorial sum of the first phase voltage plus the second phase voltage is actually at 30 degrees. Okay, vectorially. Okay, so if we now try to remove the angle, we'll just use the absolute value. Okay, the absolute value. BEB is actually line-to-line voltage. Okay? And this is actually phase voltage. Right? So in general now, this is VAB, right? So VAB is actually square root of 3 times the value B. Right? Similar with the value BC. If we try to take the value of B sub BC, which is equivalent to B sub L, it should be the vectorial sum of the voltage across this plus this. And still, if you try to derive it using same method, it will still come out as square root of 3 times the value of B. And the voltage across AC, okay, it should be the voltage across this plus the voltage across this. You add it vectorially, it will still come out that there is a factor of square root of 3 times the value of the voltage per phase. So in general now, for a Y-connected transformer, okay, the relationship of the line-to-line voltage with respect to the phase voltage is the line-to-line voltage is equal to square root of 3 times the voltage per phase. That is a general equation. For as long as we are living, it will not change. So the relationship for a Y-connected transformer, the relationship of the line-to-line voltage with respect to the phase voltage is that the line voltage should be square root of 3 times the value of the phase voltage. This value here is bigger than this value by a factor square root of 3. Okay? We add it vectorially. It's not, we don't add it, what you call this, just assuming it's a real number. No, it's a complex number. Right? So in general, the relationship of the line-to-line voltage with respect to the phase voltage is there is a factor of square root of 3. So if you try to Google it, okay, the relationship of the line-to-line voltage with respect to the phase voltage for Y-connected transformers, okay, there is a factor of square root of 3. So this is square root of 3 emanates from this vectorial sum. Okay, for the current, it's not so complicated. Why? The current, we'll just solve it, what they call this, by using our eyes. The current passing through the windings, as it goes out through the line, this is the line, right? Line A. Okay, this is line current. The current passing through the winding of the transformer is designated current per phase. Okay? Okay, I will try to remove this one so we can see the current. Okay? The current coming here is going out and there's no other path in which it will go, right? So whatever current coming out from the windings, it will be equal to the line current. So in general, okay, for a Y-connected transformer, the relationship of the phase current with respect to the line current is that the phase current is equal to the line current. Okay? Like what I said, for as long as we are living, the relationship of the current passing through the winding is equal to the current coming out through the line for a Y-connected transformer, right? So this should be the second relationship which is needed in the computation of the so-called Y-connected transformer. Just what you call this, remember these two formulas, okay, and you will not get lost. Okay, okay, that's it, guys. Those are the two important relationships concerning Y-connected, okay, transformers. That is voltage and current relationships. Okay, I will repeat it for the last time. For a Y-connected transformer, the line-to-line voltage is equal to square root of 3 times the value of the phase voltage. And for the phase current, for a Y-connected transformer, the phase current is equal to the line current. Okay, good morning from Los Angeles. Professor David G.